I'm still Michael, as always. And this video I would like to talk to you about, tell you about gravitational lensing. And to be more specific, I want to talk about magnification. Just to give you a heads up, my little baby girl is lying down on the floor and having a really good time with a fish, a play fish, not a real one, hanging from the top. And so if you hear some happy or crazy baby sounds, baby-like sounds, that's the explanation. So she's really happy now, so I can do this video in quiet and peace, sort of. Alright, so I jotted a lot of things up on the blackboard, the whiteboard here, a lot of math, and I can tell you right away two things. I already mentioned it in my first video. This should never ever, in any circumstances, be seen as any sort of introductory course, or something of the sorts for gravitational lensing. I am but a mere master student, so I don't have neither the knowledge or the ability to educate people in this way, in an introductory way to this subject. Not yet, at least. But you should see this video as an introduction to when I would actually like to tell you and show you some of the really cool things that I have been doing so far with modeling and gravitational lensing, and also to show you some pictures, and we can all actually have a discussion. Both I will tell you on a video, but also on the discussion board, what it is that you actually see. So some of the future videos that I'll be doing will be on my Linux machine, where I'll be taking programs in like DS9 and show you the results from a model and what you can do with it and what you can show with it, and some actual pictures from gravitational lens systems. Alright, so the subject at hand is magnification. Now I think you can already now, just by the name, get an idea of what it is. So what you have is this formula here. So what is that? It is when you have you have the total flux you get from the system. The nu here is because it's dependent on wavelength. So this is the flux from a system. Flux is when you point a telescope at some place in the sky, you will get a certain amount of light from it. So flux is, you can see it, how much, if you wanted to, like flux through a water pipe would be how many water came through a slice at a given amount of time. So this is basically how many photons that comes from any source on the sky. And the I is the, just see it, I think it's called the intensity. Yeah, this is actually not really called anything, but it describes the surface brightness of the source without lensing. No, sorry. It's described only the surface brightness of the light from the source, and the nu describes the frequency. So it's frequency dependent. You can also just convert that to wavelength if you wanted to. And the d omega is the solid angle from which you receive the light without gravitational lensing. So you can rewrite this in some ways. I'm going to do it over here. Remember this formula. I'm sorry, I'm going to be jumping a little bit around on the whiteboard. Keep calling it blackboard. All right. So you can actually make two formulas, right? You can also write a new formula. Almost the same. where I just put stars on. Sorry, I just had to check up on her. So, back to the formula. So this is the total flux you get from the system when you have a source with a given surface brightness, and you get some solid angle, that is the angle from which you get the light, without gravitational lensing. Now, if you introduce gravitational lensing, then you have to write a new formula where you say that the flux from the system is still dependent on the surface brightness from the source, but this time the solid angle depends on the gravitational lensing, and then you put a little star on the d omega, on the solid angle. So you can divide these two with each other, as I've done here, and then you get d omega. Let's just do it right. So you get S nu, sorry, that's not a nu, d omega divided by, let's do it right, okay, so S nu equal to I d omega star. So S nu divided by S nu, that's 1. This is also 1. So what you're left with is that 1 equals to 1 times d omega over d omega star, right? And then you can, if you want to, divide by 1, then you get 1 divided by 1, that's still 1. So in reality what you get from this formula here by dividing them with each other is that the magnification you get from a system, let's just put these on, is equal to the solid angle divided by the lensed solid angle. And that's what I've written up here. Now you can change the units around. So you, instead of having d omega over d omega star, you can replace them. So you get d squared x over d squared y. This means that it's a double differential or double derivative. Then you can replace these, put them in a different way, and get to that this tensor here is equal to partial xy over partial xj. So these are partial derivatives. And this gives me that the magnification is equal to the determinant of A inverse. So you can write this in another way, that it's equal to one over determinant of A. Now, one of the usual things that you can do, which is not really crucial, is that you can introduce the magnification tensor instead. And this is not a theta, this is still the A. So M is equal to the inverse of A, right? And that means that mu is equal to the determinant of M. This is just to get the basics of the math in place. Just that. So this is where I want to show you what the magnification is. So we have a lens here, and then we have a source out here, and the difference from the lens to the source is beta. Now this value was introduced in the last video. And then you have the distance from the lens out to the images, which I call theta plus and theta minus. And this is because the minus refers to the parity of the images. So you can see that the shape of the magnification from this image due to the lens gives it the same shape. You can see it's the same shape as the source. Sorry, the shape of the image is the same as the shape of the source. So that gives it a positive parity. Whereas this image down here is this image down here is magnified so that the position the shape of the image is opposite to that of the source, and hence it gets a negative parity. Alright? Now this is just two-dimensional, so it's not really correct. When you have images you usually look them, sorry, this is just, it is two-dimensional, but you have more complex shapes and more complex magnifications when you look at actual images, so you can get a different, your shapes can be much different than this. Alright, I will pause the video now and then erase the board and write something new. Alright, so now I will be finishing my little talk about the magnification with the introduction of convergence and shear. Now convergence can already be introduced by saying that you have the surface mass density dependent on some angle and the distance to a lens divided by the critical surface mass density, which is a number that can be derived by this. You have c squared, the speed of light, times 4 pi g times ds over dl dls. And as we talked about last time, if we have a source here, a lens here, and an observer here, then dl, the lens distance from the observer to the lens, this is dls, and this distance here is ds. So these are just distances, and these can be found if you know the cosmology you're working in and you know the redshift to the source and to the lens. Alright. From this you can then find the critical surface mass density, and then you have to find the surface mass density in some way to get kappa, the convergence. So when you want to find convergence and shear in order to work with it in lensing, you have to look at this integral here. So we have that this phi of theta is equal to 1 over pi, the the two-dimensional integral of theta, a mark is just because you're integrating, times kappa theta times the logarithm of theta minus theta mark over d squared theta. Again, baby trouble. Alright, so let's continue. So you can use the Poisson, hopefully I pronounced that correctly, the Poisson equation. So if you take this is the gradient, so this is partial differential, it's a double partial differential of this up here, the phi, then you get 2 times the convergence. Then by looking at it from a matrix point of view, I'm not going to do that explicitly, I'm just going to tell you, and then you can check it to see if it's correct. What I'm telling you is that you can get that kappa is equal to 1/2 of the trace of phi ij. And these denounce differentials, remember that, partial differentials. And from that you can derive that gamma is equal to gamma 1 plus I gamma 2. This means that this is a complex number. You have a real part and a complex part. Alright? And when you look at all these things, you do some really, I wouldn't call them nasty derivations, but you do some derivations of these numbers, you can get that gamma 1 is equal to 1/2 phi 11 minus phi, no sorry not phi, psi 11 minus psi 22, and then you can get that gamma 2 is equal to psi 12 and psi 21. That's the same. And again, when you do some matrix magic, you put it into a matrix and you do the derivations, you calculate the derivatives, the partial differentials, then you get that the magnification matrix or tensor, I think this is a matrix, right? It's equal to 1 minus kappa minus, this is a kappa, 1 minus kappa minus gamma 1 this is minus kappa, sorry, this is minus gamma 2. You have also minus gamma 2 here. And then you have 1 minus kappa plus gamma 1 here. And so you can write this in a different way. I'm just going to do that now, quickly. Hopefully you will get that 1 minus kappa 1 0 0 1 times minus gamma cosine of phi sine of 2 phi. Just have to check. This is also 2 phi. Then you have you have sine of 2 phi, and then you have, I think it's minus cosine, yes, minus cosine of 2 phi. So, and the phi is some sort of angle, right? When you have an image and you stretch it, then you don't have circular symmetry anymore, and then dependent on how you like take that, you can I'll tell about it here, but this is a phi. This is some sort of angle that we are working with. So from this we can see that now we have that this is the convergence. Hope this is spelled correctly. And shear here. Also this part here, right? This is the convergence. So when we have this magnification and we use a circular symmetric source, right? Then if we do the convergence alone like this, we just get some sort of symmetric magnification. You just make the image larger in the same way, like magnifying something simply. But, and this is only for a circular symmetric source, if you add shear to the problem, you see you have this phi, right? You have this angle, and you have the gamma here. Then the image, the circular symmetric image, not only gets magnified, but I'm sorry, she's just making a lot of noise right now. Alright, but I'm also almost finished. So if you add shear to this component, then you get that this circular symmetric magnified image will be shaped elliptically. And then when you have this ellipticity, you can imagine that if I say that this is my baseline, right? Then I can make a line like this, and then I have an angle here, and that is the phi. So the angle is the direction, the position, because when you have something that is shaped elliptically, it is of course no longer circular symmetric. And when it's not circular symmetric, you have to apply some way to define which position it has, where its position, its angular position on the sky. So this is basically how magnification, convergence, and shear behaves. Now, of course, the math inside this is much more complicated, and I could possibly stand here and do a long derivation using using the calculations and have it somewhere, but the real important part for what I'm going to tell about here is this part. Knowing that when you have a source and you add convergence alone, it gets magnified equally in all directions. If you add shear to the problem, then this circular source will become become elliptical, and then you add some angle to know in which direction it's positioned. Now, of course, galaxies are usually not circular symmetric. They have some shape, and then of course when you add this, a non-circular shape, into convergence and shear, you get something completely different. Usually it is, like I'm going to tell in the next video, also when you look at the problem very basically, is that when you are close to a critical line with the image, it is no longer just elliptically shaped, but it will also be bent in sort of an arc. But where this is called strong, this is real strong lensing. But when you're further out and you have weak lensing, then this will happen. Alright, thank you for watching.